Thank you very much. The mic's on. Okay, the first thing to know is that I decided to start on page 3 of my notes instead of page 1. Page 1 and 2 were sort of an overview of classical quantum simulation, and I became a little bit worried that would mean I would get cut off in the middle of the good stuff. So if there's time, I'll say a little bit about that at the very end. But the main goal here is to give you sort of a very, very elementary introduction to tensor networks and this type of classical simulation, including DMRG. If your thesis project is in this area, you'll probably just pick up a few tidbits, but it will be sort of elementary, but it's designed for the broader audience. And then the other aspect of it is that I wanted to show how easy it is to do calculations using this nice iTensor software. You can, solve a quantum system of 100 sites on your laptop if it's a chain, very quickly. And that the code is so tiny and it's very easy. So I wanted to show how that worked and get people to try it. So that's the goal. So jumping right into tensor networks, we can imagine I've told you a little bit about what some other methods are, like quantum Monte Carlo. So what is it about tensor networks? So the key problem with quantum mechanics, as we all know, is that there's an exponentially large Hilbert space that we have to deal with. And so what you have to address is how to, on a quantum computer, you don't care, you represent it. But in a classical computer, you have to know what you're going to do with it. And so in tensor networks, what we do is we compress it. So it's like it's a super large file and we want to get it down to a tiny file. Okay, so it's all about compression. Okay, so let me start writing. Okay. Compressing the wave function. Okay, so let's start with how you compress a matrix. And this has been understood for quite a few decades. And there's some different ways, but the main one people think about now is through the singular value decomposition. Or just CSVD. And that's a general factorization that applies to any matrix. M could be rectangular, doesn't have to have any properties at all. It's written as U times D times V dagger, or sometimes they leave off the dagger, it's just a different definition. The left and right matrices are as orthogonal as they can be, so U dagger U equals 1, but they may be rectangular, so it may just be column orthogonal, and V dagger V equals 1, and D is diagonal, so lambda 1, lambda 2, etc. And we normally put these in order. Lambda 1 is greater than or equal to lambda 2, etc., down to 0. So you can choose them all to be positive. Now this looks like an eigenvalue decomposition, and of course your eigenvalues could be negative, but because U and D are different, if there's a negative sign, you could put it on the other side, on say the V and not the U, because they're different. So you can choose the lambdas always to be positive. Okay, so now so we have this, you can do this for any matrix, and then if it's a random matrix, you will find that all of the lambdas are non-zero, and this doesn't buy you anything. But suppose for some reason, a lot of the lambdas are very close to 0. Okay, so if that's true, if lambda m plus 1 down to lambda n is approximately 0, then you rewrite the matrix, and let me draw it sort of schematically here. So I only keep the non-zero parts of the matrix, lambda 1 up to lambda m, and I cut off the other parts. So I sort of draw it like this. You can see it's just a few rows and a few columns. And I've gotten rid of this big square thing, and I've made it a lot more vector-like on each side. And so that can be a very big compression. The ideal case is that the matrix is exponentially large, and you can replace it by something, the number of columns and rows is of order 1. And that's actually what happens in a lot of quantum situations. So it's a huge compression. Okay, so this is, and if it compresses like this, we say it's low rank. And I was at a poster session at CCQ a couple days ago, and I noticed, and it was not just, it was all the different CCs at the Flatiron, all presenting, it was the summer interns, and I noticed about a half a dozen of these posters had low rank in their titles. So it's a very, very well-known thing, you know, in machine learning, et cetera. Okay, so the question is, okay, why would you have anything that's low rank in quantum mechanics, and how do you utilize that? Okay, so let me now start introducing diagrams. So this is one way of drawing matrices, but for tensors, we'll want to do a very simple notation, where this M is just a dot with 2 lines sticking out. Okay, so a matrix has 2 indices, and so indices on an object are just lines sticking out. Usually I won't tell you what they are, and then the object itself, it's like sort of represented by the dot. Okay, and so this SVD is just that, this matrix equals the product of 3 of them, which doesn't tell you too much. You can make up a different notation for a diagonal matrix, like a diamond or something like that. And you know, you can decorate this, and you can put arrows on them, and that's all useful. But we won't worry about that too much. A key aspect of this notation is that when you multiply matrices together, you don't really care what the names of the interior indices are. And so an interior index is just a contracted line, and we don't even separate them. We just draw it like that. And you know, it's just there, and you know that there's something there that gets contracted over. Okay? So it's doesn't do you so much good for matrices, but for tensors, it can simplify the notation a lot. Okay, so now let's go and be a little bit quantum. So let's talk about a wave function of some number of spins or qubits. Okay, so the tensor diagram notation we might write it like this. So each line coming up is the states of a qubit, S1 through SL, say. And then we're not putting any restriction on how this wave function is set up. It could be totally dense. And so we put a big box, that's the equivalent of our dot. That means that that's totally arbitrary. Okay. And so now the SVD only works, it's only defined for matrices directly, but so how do we make this into a matrix? And this is not an operator, so you might think, oh, it's an operator, I have the input and the output of an operator, but this is just a wave function, so you don't think of that as a matrix. But I can draw a little line between it, and I can always regroup sites together into a fat line. So instead of 3 different qubits, each with 2 degrees of freedom, I just make it into an 8-dimension index. You know, and so that's nothing to that, and I make this into a matrix like this, and then I do an SVD. Okay, so I'm left with something like that. Okay, so I can certainly do that with any wave function. The SVD will work. In this case, you know, it wasn't even square, so I can put more spins or more on one side than the other. I can do this, and then the question is, well, do I get anything out of that? Does it compress? Okay, and if it does compress, so if I do it with a truncation, and then this dimension is only a number m, you know, if m is of order 1, then what do I get out of this? I get a compression from the original thing is 2 to the L down to, I have 2 guys and they're of dimension, they still have L over 2, but with an extra M. Okay, and so that was just the 2 of them, and then this dimension of that. Okay, so this is a quadratic sort of compression, like these quadratic algorithms, not an exponential one, so we're not done yet. We want to get it all the way to an exponential compression. But this is certainly a lot of progress. Okay, so why might a wave function compress like this? Well, if it's a random wave function, or if this wave function came out of your quantum computer while it was doing Shor's algorithm, it's not going to compress, right? So random things never compress. You know, it's just by the nature of random things, you can't compress them. Shor's algorithm, the algorithms tend to be, you know, they try to utilize the entanglement in the qubits as much as possible. And so if you write an efficient Shor's algorithm, it's going to scramble up everything, and you're not going to be able to compress it. Okay, and so we're not talking about a universal replacement for quantum computers, but let's think about instead ground states of Hamiltonians, and let's think that they're sensible physical ground states. Okay, what's sensible? What's the characteristic of physical ground states? Well, they come from physical Hamiltonians, and the Hamiltonians that nature gives us are things that have local interactions. Like 2 spins nearby, they interact with each other. You don't have, you know, this spin interacting super strongly with somebody really far away unless it's part of some sort of collective mode, like a Coulomb interaction. So they're local, and it really introduces a lot of simplicity into the problem. Okay, and so that's and we also tend not to have, you know, interactions that simultaneously have 100 spins interacting with each other simultaneously in the worst possible way. So our Hamiltonians are very simple, and ground states are designed to optimize that Hamiltonian. You're trying to get the lowest energy. So that simplifies things a lot, okay? So we can, instead of looking for the worst case, which just doesn't get us anywhere in this case, let's look for the best case. Okay, a lot of times you make progress by saying, is there something that I can make an algorithm for the easiest case I can think of? And if it's a new thing that somebody hadn't thought of, you know, you've solved the problem. So let's say that we have, suppose we have the left side is A and the right side is B, and suppose they are independent. Okay, so if they're independent, what does that mean? Quantum mechanically, it means that you have a product state. So this wave function of both is the wave function of A, the wave function of B, and they're just multiplied together. Okay, if you look at what the SVD is doing, you can see that what it really means is that the inner matrix is essentially 1 by 1. You just have the vector for the left times the vector for the right. Okay? And so this corresponds to m equals 1, and then we say this is unentangled. Okay? And the definition of entanglement is basically sort of how far away are we from a product state. Okay? Sometimes this is a little bit tricky because you might not recognize yourself as being in a product state because, you know, if you look at the 0 state in the x direction, you know, it's 0 plus 1. And if you multiply that all out as a wave function for 2 spins, you would see it's got all 4 terms and it doesn't look unentangled, but it is, and the SVD would reveal that. Okay, so for an entangled state, we can think of our good friend, the singlet, or Bell state, 1 over root 2 up, down, minus down, up. Okay, and this is already in Schmidt decomposed form. Sorry, the SVD, which is this is synonymous with the Schmidt decomposition. And that's just the quantum information term for decomposing a wave function with the SVD. Okay, so this wave function is in the Schmidt decomposed form because the states for the left spin on the two pieces are orthogonal to each other, and the same for the right. And so that means it's actually just sort of an SVD. We just have to put this sign into one side, so I can write it as 1 over root 2 up, down, plus 1 over root 2 down, and then minus up, right? And so the lambda 1 and lambda 2 equals 1 over root 2. Okay, and notice that if I sum the lambdas, the normalization of the wave function is going to tell me that the sum of lambdas quite generally is equal to 1. Okay, so the question of entanglement is just what are these lambdas doing, right? And in this case, these are two equal singular values. So this is the most entangled. This is the maximally entangled state. Okay, and so that's an example of something that is in the wrong direction in terms of you know, our SVD having the minimal thing. It's certainly entangled. Okay, so we can draw sort of pictures, cartoon-like pictures, to try to get a sense of what typical ground states are doing. Again, thinking back local interaction terms, and the simplest I might think of is like S dot S, a Heisenberg interaction between near neighbor spins. Okay, and I can draw pictures of that and say, well, you know, what would a ground state look like if it's trying to optimize the S dot? So each term in the Hamiltonian is trying to make that pair, if it's a Heisenberg interaction, is trying to make it into a singlet. The trouble is that they can't all be singlets with everybody all at the same time, right? There's this idea, or this you know, well-known thing in quantum information called entanglement monogamy. Okay, so what is monogamy? That's where I don't cheat on my wife, right? And so I'm married to one person, and I don't try to marry another person at the same time, and I don't cheat on them either. Okay, so that's monogamy, and so spins, you know, in sort of a certain well-defined sense, which I won't get into, are monogamous. And the simplest example of that is if I take a triangle of spins, which one, you know, have our Heisenberg. So this is your classic example of a frustrated spin system, because each leg of the triangle wants the spins to be opposite, and so you satisfy two of them and you can't satisfy the third. Okay, and so that frustration is sort of built into this idea of monogamy. So if you diagonalize this simple system, you find that its energy is minus 3/4 J, which is the same energy as if there were only two of them. So the extra spin is just kind of stuck out there. It doesn't get to get married to either of the other two guys. They're married and that's it, right? So entanglement in systems, as a general rule, you can't just entangle with everybody, okay? And so quantum systems are always struggling to sort of optimize their local entanglement, and that's how they get a good ground state energy, and a lot of times they're frustrated in some way. Okay, so so the cartoon picture for this is that if I had a cartoon of the ground state is I draw some dots like this, and I say, okay, those two are in a singlet. Oh, maybe this one's longer ranged. And then maybe this guy, they're sort of doing that. And then these guys are near neighbor, and et cetera. This is sort of our simple picture of what a ground state looks like because of the nature of the Hamiltonians. Okay, now when you draw a dividing line, an artificial dividing line between the system, okay, so suppose I cut the system in two. And what is that dividing line? It's just the place where I group the indices into two pieces. Okay, so the states here that are in a singlet, those are tied up together and they're totally inactive in terms of participating. Their entanglement is all entirely on the side that they're on, okay? So there's no entanglement from this. They do not contribute to the singular values that are non-zero, and the ones that are non-zero are the ones that are cut, okay? So it's just those sort of bonds that are cut by your imaginary line that contribute to making entanglement and contribute to sort of making this SVD not, not low rank, okay? And so it's like this guy is the only contribution. Now this little picture of this is sort of a cartoon from the valence bond picture, which is a valid representation of many sets of states if you do a superposition of them. And but I'm using it just as a cartoon, okay? But you can think of as like, oh yeah, we're gonna do a resonating valence bond state where it's a superposition of drawing the bonds this way and drawing them a whole bunch of other ways, but they're mostly short-ranged. And but the result of that is that systems tend to have low entanglement, and the Schmidt decomposition works very well. Okay, and so what that will mean is that if we plot the lambda I versus I, so the worst case, this is the worst, is that all the probability is divided between these different pieces, and the best case is everything is sort of in a one case. And then the case that we're interested in with tensor networks, which is more complicated than the product state, is this. Okay, so that's what we're sort of hoping for. Okay. Okay, and I'll show you a plot with that in a little bit. Okay, so how do we get exponential compression? Okay, so I've already split it into, let's say I divided it in the middle and I split it. And let's say that I had a good approximation where I could keep, m states or m indices in the middle, and that was a small number. Okay, so I split it like this. Okay, so I look at one side, and I split this into something that looks like, so that's coming out here, and I group these together. So there's one index coming out there, so it's really that coming there, and then everybody else is together. Okay, so I try to split off not only the middle link, but also one extra spin. Okay, now the SVD on this is going to act essentially almost the same as the SVD in the original case. If there's low entanglement, that low entanglement will apply towards this other bond also. And so this SVD will give me something that looks like this, again with, say, of order m states. And I split one side off, okay? So here's this extra site. Okay, and then I can repeat this with the other ones and work my way along. There was a question, and you got the, yeah.
Yeah. So I was wondering that, so you first divide the entire thing into two pieces, right? So, and then you take the say the right piece and you go from the left side. But so why not divide the right piece also into two? Like why not do like a, because they'll cut the problem into half.
That might be more efficient. Okay, so the reason I didn't explain it that way was I wanted to get this smallest piece right away. Okay, but you might do better that way. Probably be a little bit more efficient. Okay, so you can cut it in two and then keep chopping. The key thing is you get to keep doing this until there are pieces that all look like this. Okay, so that's the basic unit that we come down to, and that's what gives us the exponential compression. So here's our basic tensor that's in a matrix product state, okay? And our whole state then looks like this. Okay, so now you see the nice diagrammatic notation. So it's each dot is a separate guy, it's a 3-index, guy, but the top one is only 2, so it's like 2 m by n matrices that you just store. And then, on your computer, you just store this in a big array. And that's all the storage you have. So for a 100-site system, and if the bond dimension, this m is called the bond dimension, is 100, okay, you have 100 100 by 100 matrices. So you can store that almost in a calculator, right? It's a tiny, certainly your phone. Yeah, very easy, very simple. Versus 2 to the L, okay? So it's 2 to the L versus L guys, and each is of order 2 times m squared. Okay, so that's the exponential compression in this case where everything is working well. Okay, so this is a matrix product state. Even though it's got 3 indices, we think of it as it's like the vector of polyspin matrices, which have an extra, the vector index is an extra thing. It's like, oh yeah, there's an up and a down or a 0 and 1 matrix on each slot, okay? And you can think of it, one way to think about a compression of an object is like, okay, so I have an exponentially large number of possible index values that I could give it. So suppose I gave it a bit pattern, 0, 1, 1, 1, 0, etc. Can I get a number out of that? And that's as easy as can be. You stick the number on each part, and it sort of gets rid of that index and gives you a choice of which of the matrices that you had, plus vectors on the end. And so you just multiply all the vectors. It's just a vector matrix multiply that you contract, and you get your number for the wave function. Okay, so you can always evaluate the psi of one particular sort of component very easily. Okay. Okay, so to characterize this, to characterize how entangled something, then we define an entropy, and so von Neumann wrote down von Neumann entropy, which just depends on the lambdas. So the von Neumann entropy is not a property of a Hamiltonian, but of a wave function, and it's also a property of where you draw the imaginary lines separating the two pieces, okay? And S En is minus sum on I lambda I squared log lambda I squared. Okay? And if you think of lambda I squared as being a probability piece of I, then this is the statistical mechanics formula for an entropy from information theory. And so it's just a way of characterizing this behavior over here. If all the weights are the same, then this you can think of as the average of log lambda I squared, the minus sign. If they're all the same, then you just get an n over 2 log 2. For for a system with of qubits. So you cut it in two, so you only look at half of the system, and this is what you get as the maximum. And so then the question is, what do you get? And if you have this case, one lambda, then you get s equals 0. Okay. Okay, so let me show you some of my, first one's one of my favorite slides of all time. Let's see if this pops up. I need to have the screen lowered. Right. Okay, very good. Okay, so what are we looking at? So this is a simple little calculation I did myself, more than a decade ago. But I just wanted to sort of, I did it for a talk, and I wanted to just sort of show a few things. So first of all, so what is it? It's a spin chain with either 8 or 12 spins. It's got a Heisenberg model with a little bit of perturbation to it, a little bit of random potential to it, so that you can see all the levels instead of them being on top of each other. And then the vertical is just the energy. And so the first thing you see is, oh yes, there's exponentially many of them, right? So it's just like, and they're sort of spread out at the edges, and then the middle is just, they're stuck together. And there's a lot of them. Okay, but then for each of those, so that's from a full diagonalization of the Hamiltonian. So then for each of those, so I plot them with the energy, so the ground state is this one, and then the entanglement entropy from splitting it right down the middle. Okay, and this is for the case with 12 sites. Okay, so what do you see? Well, a perfectly classical system would have entropy 0. The ground state is not that. The ground state is up there, and it has a much smaller entropy than it could have. So the top line above it would be the maximum it could have. And then there's sort of an envelope that as you go towards the middle of the spectrum, the entropy is much larger. But so you can see that ground states are sort of special. They are certainly not perfectly classical. There are two states here that are perfectly classical. Where are they? Why are those? Why are they perfectly? What are they? Ferromagnetic states. Yeah, those are at the top of the spectrum, and they have the random potential, so they're a little tweaked, so that you can see both of them. That's the all up and the all down, right? Okay, and so everybody, so now we would consider, before the modern day of, we have a number of classical methods that can solve these sorts of spin systems nicely, including DMRG, but this was considered a highly, this was a highly non-trivial state, this ground state. It's strongly correlated. It's got lots of interesting quantum effects. But on the scale of true quantum entanglement, it's very small. Okay? And if you look up at the middle top of the spectrum, these states which really have a lot of entanglement, there's no classical algorithm besides this direct diagonalization that can touch those, right? There's no simplifications for those. They're so crowded together, the Heisenberg uncertainty principle says that it would take exponentially long to separate them out with some sort of, dynamical process, okay? So it's like they're monsters and you can't touch them. And probably they're also, because they're weird eigenstates, which are just incredibly complicated, you probably can't even touch them with a quantum computer either. Okay, so those are sort of non-physical. But anyway, so this is sort of showing that we do have low entanglement in ground states, a lot less than it could be, and so we can try to take advantage of that. But there are regimes where it's just not going to work. Okay, this I wanted to show, this repeats some of what I said, but I just wanted to show what the lambdas are doing. So this is a 100-site spin chain with, and this we couldn't do exact diagonalization with, and so this is done with the MRG, which will spit out the lambdas, and you can see what they're doing. And if your cutoff is 10 to the minus 10, then you can keep on the order of about 75 of them, and that's the sort of M that we're looking at for one of these systems. And you can see that it sort of fell, just sort of like what I described. Okay, and then this sort of shows the idea of repeating this to get a matrix product state. Okay, so the third slide I want to show right now is what happens versus the system size, sort of in a systematic way. And so this has two different systems, a spin 1/2 chain and a spin 1 chain, where it has the 3 states plus or minus 1 and 0. These are very interesting systems that have been studied a lot. The entanglement entropy, the maximum that it could be, is shown. So this is a split down the middle, and the maximum is shown by the 2 nearly vertical lines. Okay? And the entanglement entropy is much lower. For the spin 1 chain, the entanglement entropy is not increasing with the system size. So the red dots have gotten flat. It's got this funny bump, and the funny bump has to do with some interesting edge excitations, which can be entangled, but on a big system, they'll lose their entanglement. And so the entanglement entropy, because these edge states, actually goes back down, and then that's flat. Okay, and then the spin 1/2 system, it has a logarithmic growth of the entanglement. And so you can't see it really well, but that's this slight growth here. And so that's understood to be a logarithmic growth with the system size. In principle, you could worry about that, but in practice, it is not too big a serious concern. So anyway, that's that. Okay, so I'm done with this for the moment. Okay, so how do we do things with these matrix product states? Okay, so we assume we're in a situation where they're useful, and we want to manipulate them. The simplest sort of thing, so manipulating. Okay, so the simplest thing you might do is calculate the normalization of a wave function written as an MPS. Okay, so that's of course sum on S1, S2, etc., psi star S1, S2, etc., and I'll write them separately, psi S1, S2, etc. So the diagram for this, we usually draw it like this, one above the other. Okay, and lines connecting. Okay, so the lines connecting them tell you that the two pieces have the same indices, which you see in the formula. Okay, and so that's a line like that you can also think of as the identity operator. So it's like you're contracting it with the identity operator. Okay, so this sort of two-layer sandwich is this normalization. The key question about working with this is how do you contract it? Okay, so there are an exponentially large or a very large number of bad ways to contract, right? Let's think of let's think of just multiplying a set of matrices. Okay, so that's the diagram for multiplying a set of matrices, A times B times C times D. Now, I don't know if anybody has ever worked with someone who's written a code to do a contraction like this where they did a nested, if there were 10 matrices, did they do 11 nested loops to sum over all indices together? But that would be sort of the worst possible way that you could contract a set of matrices. But what we all know is that you just do it with temporaries. You multiply the first two, and it's replaced by one matrix, and then you multiply the next one, et cetera, and you work your way along. And you have to, have an extra storage, but, you sort of don't go exponentially bad. So the equivalent here would be maybe I multiply out the whole MPS on the bottom and then do it on the top or something. But so, of course, what we do is we work our ways left to right. Okay, so I multiply those two tensors. That's just like a matrix multiply. Okay, then I add one to what I already have. And so there's sort of a bubble diagram that you draw that sort of shows how you're going to contract them. And so you make a new temporary which has this next one put in. That's like a matrix multiply 2. And then you do this one and that one and this one, et cetera, and you work your way across, and it's all just equivalent to matrix multiplies. In other words, the calculation time is m cubed times the number of tensors you're putting together. Now, I'm not going to talk much about a general tensor network, something where I just sort of put a bunch of nodes and draw lines between them and say, each one is a tensor. It's known that the best order of contracting a general tensor is hard, NP hard or something. And so that is difficult, but in the cases where we work with just matrix product states, it's like, no, you always work left to right. Okay. Okay, what about an expectation value? So let's say I did SZ on site 4. Okay, so that looks like, so I count along 2, 3. I put my SZ operator at site 4. Okay, so this is SZ. Okay, I put that in there, and this is, and you can, again, think of, when we're working with these operators, it's like you have identities on all the other sites, and those are just these lines. So you can do any sort of product operator like that just by inserting the operator like that. Okay, and you can work your way left to right. Okay, but you can simplify it even more. I mean, this is a contraction that goes over all the sites. In terms of practical calculations, it's important to take advantage of sort of a gauge ambiguity in the definition of a matrix product state. Okay, so suppose I look at just 2 of the tensors. There's an A1 and an A2. Suppose I took a matrix and a matrix inverse in between those. So this is a U and a U inverse, and stuck it between them. Okay, and then, so obviously, this matrix inverse doesn't do anything to the overall values of the matrix product state. It's completely equivalent. But this now gives me an A1 tilde, and this guy gives me an A2 tilde. Okay? And so there's exactly equal to each other as a matrix product state, but they have different tensors. Okay, and so you can do that anywhere. What we do with this extra degree of freedom is we make use of it to simplify the calculations. Okay? So it turns out that it's easy to pick the U, or in fact, what usually happens is that when you get these tensors and you do an SVD, it automatically gives you a certain orthogonality to it. And so we can choose. So this corresponds to equivalent to like U1 equals U dagger U. If from an SVD, it looks like this. So this is A and A dagger. Okay, and we say that this contraction is equal to that, which is just the identity. Okay, so we can choose it. An SVD will give you an orthogonality that looks like this for the left-hand side, and for the right-hand side, it will give you the reflection of this. Okay, and generally it's easy to choose one or the other of these. And so what we generally do is we choose the gauge so that all the matrices to the left of a certain center point are behaving this condition, and the ones to the right are behaving this condition. And if you do that, this gets rid of the contractions like this. So this thing becomes that. Okay, well, you just work your way, you apply it all the way to the left. So you work your way and you just get rid of the two outer tensors and replace them by a line. Okay, and then that allows you to apply it to the next one, and so you're just applying this equation left to right, and it gets rid of all of them, and so you get to evaluate a local property without paying attention to the rest of the wave function. You just have this particular site. This site that we choose dividing between the left and right is called the orthogonality center. Okay, or OC. Anybody heard of the OC? That's the name of Orange County in California. It's like, that's where I live. So, so I like this, it's like the OC. And then I was telling this to a set of diverse students once, and they said, "Oh, but we don't know how to pronounce that word." So orthogonality, just put the emphasis also on O, and everything else works out right. So anyway, so that's something that we make use of whenever we can. It applies even when you think of complicated tensor networks. If you can define the equivalent of an orthogonality center and make everything contract in around that, then your algorithm's going to be pretty easy. You can just focus on local things. Okay. Okay, in doing these contractions, so if they're near neighbors, you get to contract all the way down to this. And if they're farther apart, you have to put the lines in between. You can't get rid of them. Okay, and so these ones in the middle are sort of telling you how correlation functions behave. So when we do SZ at distant places, it's like, oh, there's some correlation that will make those fall off. And all of those correlations are built in to the transfer matrix, which looks like one of these guys. That. Okay, and so you can analyze correlations with those. Okay, Hamiltonians. So, of course, Hamiltonians are just collections of operators, but it's a sum of them. So if I have something that looks like this, and maybe, it's got identities. Okay, that would be like SZ times SC on the first two sites, and then maybe I put them on the second sites. Okay, and there's a lot more terms in a Hamiltonian. Okay, one of the nicest things you can do to organize calculations is to combine all the pieces in the Hamiltonian into something called a matrix product operator. Or an MPO. So what this is it's just the equivalent of a matrix product state, but it has two indices on each site, and so one sort of the input and one sort of the output. Okay? And so this would be the MPO representation of our Hamiltonian H. Now, Hamiltonians, we know that when we work with them, they're simple things unlike the wave functions that they produce. So these are very easy to work with. There are rules for putting these together, constructing them. And in fact, in iTensor, one of the nicest things about it is that it has the simplest interface for making the MPO of an arbitrary operator. And so I'll show that in a little bit. Okay. Okay, so once we have written our Hamiltonian like this, then we can think about algorithms where we don't have to pay attention to the details of it, but we just can think of it in this sort of, the same sort of language, the same sort of representation as our matrix product state wave function. Okay, so the expectation value of psi h psi is just a 3-layer sandwich, right? Okay, so very natural. How do you contract it? Well, you work left to right, right? There are so complicated Hamiltonians like you get in quantum chemistry calculations. Those have a lot of terms, and that's reflected in a big bond dimension for the MPO. Okay, and so that is something that goes, maybe in the thousands, and it goes into the cost of doing DMRG in a quantum chemistry basis. Okay, so how about finding ground states? Okay, so the problem, of course, is just to minimize psi h psi over psi psi, or constrain psi psi equals 1 without the denominator present. Okay, so if you asked a machine learning person how to do this, what would they say? Gradient descent. Using automatic differentiation. That's what they do for everything, right? Right? It's a wonderful technique. Yeah, it's a wonderful technique, and tremendous progress in that. It's still lousy compared to what DMRG does, right? Gradient descent uses vast fractions of the world's electrical power, and if it was as good as DMRG, we'd be able to do it with our household outlets and stuff. It would be fine. Okay, so so this just doesn't work. It's just very slow to get there, and of course there's a local minima and stuff. Another way to do it, which is much better but still not as good as DMRG, is imaginary time. Okay, and so this is okay. So how does that work? I don't have too much time. Okay, so this is a good stopping point to ask for any more questions, and then I'm just going to continue straight on after the break. So, question.
So I've got two questions. The first one is that it's kind of counterintuitive to think that a vector-vector multiplication or matrix-vector product is less efficient than matrix product, as what I'm seeing is happening in.
Which part are you looking at?
No, I mean earlier you have the matrix product state, right? So you're doing matrix multiplication. So let's say you're trying to find the H chi, and you're doing some kind of matrix multiplication. I'm just thinking that why is that more efficient than a matrix vector product? So
the matrix vector would always be better if you could do it. So if I do a sandwich, do I have a sandwich? Well, let's take this sandwich. Right? I challenge you to draw some bubbles that gave you matrix vector. You will not find it. It's whatever line I have, if I draw a line, it's two lines sticking out. So and they're coupled. So it's, it's matrix in this. There are some algorithms that are matrix vector. There's a sampling algorithm that's matrix vector. Very important if you've heard of it, but that's matrix vector, so it's much faster.
Okay. And this second question was that, I'm not saying what is the usefulness of the diagrammatic approach. How is that better than how we usually write quantum mechanics? So what does this gain us?
So it's just a way of organizing the algebra.
Okay.
And it depends on how you think. And I know people who are super good at algebra and they don't think in pictures. And okay, go for your algebra. I like diagrams where I just sort of see what I'm doing in this visual way. And a lot of people do. And so, but this is just to organize the calculations.
Okay.
And it makes it much quicker to explain. If you can follow this, then I can, the algebra for each of these things is pretty messy. And I can just draw a quick diagram and explain it quickly. But it's not anything different. There was a time before we had these diagrams, and there was some messy algebra that we struggled to do simple things because it was just sort of algebraic.
But so when you're doing the computation, it's not anything different in that? Okay.
No.
Thank you.
So in our compression of this wave function, we have left edge and right edge. For physical point of view, we sometimes don't want some edges, so that make it periodically symmetric or translation symmetric. Can we construct such kind of MPS?
So that's a really good question. It's fairly well known that DMRG doesn't much like periodic boundary conditions. From the entanglement point of view, if you just do the most naive thing, if I have this guy, okay, and then I say, well, what is the entanglement entropy from cutting it in two? So I make an imaginary line that has to cut the whole system in two, and I do that. I get two cuts, okay? So I get twice the entanglement entropy, which of course is a square in the naive estimate. Okay, so that makes it less friendly. And so then people have said, well, okay, isn't there some way around that? And the answer is that there are more, things that it took the people years to figure out to learn how to work with periodic boundary conditions with about the same efficiency as open. Okay, so I'm not going to try to explain those. I have one that I developed a while ago with Hans-Gert Everts, it's nice. And there are some new approaches with belief propagation that is working out very nicely, but it's a little bit more complicated. Yeah. And then if you're trying to do a 2D system, which is the modern applications, then you're talking about a torus, and then that's even worse. So